Hi everyone, welcome back. Today I'm going to be running through the TUT questions for week 10 for STA1000S 2017. This week we're dealing with the T distribution. So it's the distribution that you're going to be using if you do not know the population variance, in essence, and you deal with the sample variances. So jumping straight into question 1, so the relative efficiency of two till operators as supermarket is being assessed. The following figures relating to the number of items processed in a half hour measured of items processed in a half hour measured. Sampling 8 half-hour periods, till operator 1 processed 210.2 units on average per half hour with a variance of 14. So that variance is the sample variance, not population variance. Till operator 2 had 12 half-hourly samples and processed an average of 205.4 units per half hour with a sample variance of 10. Is till operator 1 faster at processing items than till operator 2? Identify and conduct an appropriate test using the modified approach. Okay, so I think the best thing to always do is just list what we've got. So we've been given two sample sizes. So for till operator 1 we have a sample size of 8, and for till operator 2 we have a sample size of 12. We have means for both these, sample means for both these. So the sample mean for till operator 1 was 210.2, and for till operator 2 was 205.4. We also have the sample variances for both, which they've given us. So the sample variance for till operator 1 was 14, and the sample variance for till operator 2 was 10. Okay, awesome. One other thing that I think we should also calculate quickly is, because we're going to be testing whether one is different to the other, it's going to be essentially a two sample test, is that we need to find the pooled standard deviation, the pooled sample standard deviation. So this is where one of the assumptions comes in. We're going to assume that they have the same population variance. So to find the pooled sample standard deviation, you're just going to have to apply the formula that you can find in your textbook, which will be n1 minus 1, because we lose a degree of freedom, times the sample variance of the one sample, and then n2 minus 1, so the sample size of teller 2, the degrees of freedom, because we lose one, times the sample variance, and then over the total degrees of freedom, which will just be equal to the sum of both population, or the sum of both samples minus the degree of freedom from each. So it'll be minus 2, so minus 1 times 2. We have all this information nicely set up for us, so we're just going to pop it straight in. So we're going to have 8 minus 1 times 14 plus 12 minus 1 times 10 all over 8 plus 12 minus 2. And pop this into our calculators and find out what that is equal to. So we have 7 times 14 plus 11 times 10. So that's 208. And I think we can do this in our head. So 8 plus 12 is 20, minus 2 is 18. So we're going to be finding the square root of 208 divided by 18. And we end up with 3.399. So there you go. That's our pooled standard deviation, our SP, which we're going to have to use for this two-sided t-test, because we do not have the population variance. So this is the standard deviation that we're going to be using in our test. So now let's get down to actually writing down our hypothesis test. We've been told that it's going to be the modified approach, so we're going to be looking up the p-value and not testing it against any rejection regions or anything like that. So H0, what is our H0? So is till operator 1 faster at processing items than till operator 2? Okay, so from that we can tell it's a one-sided test, because we want to know whether till operator 1 is faster than till operator 2, so it'll be a one-sided test. And so our H0 for this will just be mu1 is equal to mu2. So we're going to assume that these are equal, because that's what we're going to be testing. So our alternative would be mu1 is greater than mu2. So mu1, so till operator 1, processes more units on average than till operator 2. So this is our alternative hypothesis. We've got everything now to just pop it straight into our formula. I'm going to do this on a new page. And so essentially the formula that we're going to be using to find our test statistic is equal to mu1 minus mu2 minus, x bar 1 minus x bar 2 minus mu1 minus mu2. Alright, so it looks essentially the same as when we were dealing with the normal table, but now we're dealing with the t-table. We now then have the pooled sample standard deviation times 1 over n1 plus 1 over n2. And there you go. So that's our formula. Very, very similar. So now getting into popping our values in, we have 210.2 minus 205.4 minus 0, because remember from our assumption, our h0 assumption, we're going to assume that these two are equal, so mu1 is equal to mu2, so they just cancel out, they become 0. We've got our pooled standard deviation, 3.399 times the square root of 1 over 8 plus 1 over 12. There you go. Sorry, a bit messy on my side. Okay, awesome. So let's pop this straight into our calculator. We've got 210.2 minus 205.4 divided by 3.399 times the square root of 1 over 8 plus 1 over 12. And we end up with a test statistic of 3.094 with a bit of rounding. Awesome. So we now have this test statistic that we can look up, but we've forgotten our one last step. We need to find out how many degrees of freedom are we looking at. So remember, for looking at both, we essentially have to look at the sum of n1 minus 1 plus n2 minus 1. So we've done this previously when we calculated the pooled sample standard deviation, and we found that the pooled, or the total degrees of freedom was 18. So we know our degrees of freedom was 18. So we now have to take a look in our t-tables whereabouts with 18 degrees of freedom we can find this value over here. So 309.4. So I've got, so that's the F distribution, my mistake, chi squared. Okay, here are t-tables. Okay, so we now look down the left side for our degrees of freedom. We find 18 degrees of freedom. Get my ruler out so I can. There we go. So we've got 18, and now we just have to find whereabouts this lies, or between which values. I mean, that's usually how you're going to be doing it in this course when you look up values in the t-table. It's going to usually lie between two p-values. So we're going to go. Okay, so it looks like 3.094 lies between these two values over here, and these two values correspond to 0.5% and 0.25%. So very, very small p-values. So we know that our p-value is going to lie between 0.0025 p-value and 0.005. So incredibly small p-value here, really, really small. And so what can we conclude based on these results? So they haven't given us a rejection region to figure out or look up, or a certain p-value at which we'd have to reject. So, however, because this is such a small value, it's less than 1%, we'd reject H0. So, based on the incredibly small p-value, we would reject H0. You can maybe say at the 1% level, at the 1% level of significance. And we could then conclude that till operator 1 processes more on average than till operator 2. And so you could say mu1 is greater than mu2. There you go. So average processing for till operator 1 is greater than average processing of till operator 2. Okay, awesome. So that was question A. We've done question A now. So let's jump into B. What assumptions did you make in order to conduct the test above? Quite an important question to ask. So the first one is, I think, quite important. That both samples are independent of each other. So that sample 1 doesn't interfere with sample 2. That's quite an important one when you're doing these comparisons, because you don't want the one sample to have any effect on the other sample, and vice versa. The next or second assumption that we can make is that they're both drawn from a normally distributed distribution. So that they both essentially follow a normal distribution, both populations. So till operator 1 and till operator 2, they both follow a normal distribution. And I think lastly, probably the most important one, which allows us to use this pooled standard deviation, is that both variances, that the population variances are equal. We might not have it, but that's why it's an assumption that we make, that they are both equal. Okay, so those are the three assumptions. I'm just going to quickly maybe say so. Independent samples. We've got the populations are normal or normally distributed, and that variances are equal. Okay, awesome. So there you go. There's our three assumptions that we're going to have to make. Quite important. What would you conclude at the 1% level of significance? So we kind of jumped the gun a bit in question A, where we did actually say that we would reject it at the 1% level of significance. And so that's essentially what they're asking for. So what would you conclude at the 1% level of significance? We would reject H0. We reject H0. Mu1 greater than mu2. Mu1 greater than mu2. Greater than mu2. Okay, awesome. So now we have our last question, D. Question 1. Suppose you were conducting the above test in order to test for some unknown difference between the till operators. Okay, so previously we tested whether mu1 or till operator 1 was faster than till operator 2. Hence we had a two-sided test. Now they're saying test where there's a difference. So difference could be greater than, it could be less than. So our testing essentially becomes two-sided. How would your test have been different? So our H0 remains the same, with mu1 is equal to mu2. However, our alternative hypothesis, H1, becomes different in the sense that it's now mu1 does not equal mu2. So it's a two-sided test. Our test statistic stays the exact same amount of degrees of freedom, also equal to 3.094. There's no difference there. The only thing that differs, because remember the one-sided test, the p-values we found were 0.0025 p-value and 0.005. Now on the two-sided test, I'm sure you guys can all figure this out, we have to double our p-values. So we look them up for one side, we have to double them. So that then becomes 0.005 p-value and 0.01. Okay, and so if we might have kept our 1% level of significance, which we're testing at, we would still reject it because our p-value is not equal to 1%. It's less than 1%. It lies between 0.5% and 1%. So our conclusion doesn't change at all. So in essence, the only thing that's changed with this two-side test is H1 and our p-value, which becomes double. Okay, awesome. So that's question 2, done and dusted. Let's now jump straight into that was question 1. We're now going to do question 2. Okay. So A petrol company claims it has included a new additive in its petrol that can reduce fuel consumption in vehicles. The published fuel consumption for a particular model of vehicle has been specified to be 9.6 litres of fuel per 100 kilometers. To test the petrol company's claim, the same model of vehicle was subjected to 14 mileage tests, with the petrol having the additive, each having a distance of 100 kilometers. The average of these 14 samples with the additive yielded a mean fuel consumption of 9.3 litres per 100 kilometers, with a sample standard deviation of 0.64 litres per 100 kilometers. Does the petrol's company additive effectively reduce fuel consumption based on the sample evidence? Identify and conduct an appropriate test at the 5% level of significance. Okay, awesome. So, information they've given us. So they've told us the published fuel consumption for a particular model of vehicle has been specified to be 9.6 litres. So when they say something has been specified for, here they say specified for a particular model, so it essentially should apply to all models. We're looking at a population parameter. So in essence, they've given us mu. So mu is equal to 9.6 per 100 Ks. To test the petrol, they've taken the same and subjected to 14 mileage tests. So we know there's a sample of 14. So n is equal to 14. With the average of these 14 samples, so the average of the samples, we're looking at x bar, is equal to 9.3. 9.3. With the sample standard deviation of 0.64. Okay, so they've given us the sample standard deviation of 0.64. Okay, maybe also remember per 100 kilometers. 100 kilometers. Always remember to put your units in. Okay, so does the petrol company's additive effectively reduce fuel consumption? We're going to be using our classical hypothesis test here, not the modified, so we're going to have to set up a rejection region and all that. So H0, so null hypothesis, mu is equal to 9.6. So our population parameter stays the same. Our alternative hypothesis, our H1, is that mu is less than 9.6 because less is more efficient. So it uses less fuel per 100 kilometers. Let me put that in per 100 kilometers. Per 100 kilometers. Okay, awesome. So now we've got a significance level. Our sig level is equal to 0.05. It's a one-sided test, remember? And so now we're going to have to look up what our rejection region is. Because we do not have the population variance, we only have a sample variance, we have to use the t-test. So with the t-test, we also have to find the degrees of freedom. So you've got 14n, and we lose 1 degree of freedom because we have one estimate. We have one estimate, the sample mean. So we essentially have to look up 0.05. And so to find this rejection region, we just have to look this up in our tables, our t tables. We have 13 degrees of freedom. There's my ruler. 13 degrees of freedom, and we want the 5% level. So our rejection value will be 1.771. 1771. Okay. Awesome. 1.771. Now, the value that we're going to be rejecting at is actually not this, because remember, if we draw our graph, right, the t-table only speaks about values to the right. We, however, want to focus on the left because we're looking at less than the mean. So in essence, because of symmetry, our value of 1771 becomes negative 1.771. So in essence, if our test statistic is less than negative 1.771, we would reject it. So good to remember that. So go pop in the negative in there, maybe in brackets, just that we know what we're going to be looking for. Okay, awesome. So now it's time to actually do the test statistic. Our test statistic, remember, we've got 13 degrees of freedom. This is equal to x bar minus mu over the sample standard deviation over root n. We have all of this over here. So we've got 9.3 minus 9.6 over 0.64 over root 14. We'll pop that straight into our calculator and find out what that is. We've got 9.3 minus 9.6 divided by 0.64 times the square root of 14. And we end up, I think I've done something wrong. 0.64, sorry, not times, divided by, my mistake. We end up with a test statistic of negative 1.754. Awesome. A bit of rounding. Now, what did we say previously? What is our rejection value? Our rejection value is negative 1.771. This value is greater than that. It does not lie to the left of that. And so, what can we conclude? We conclude that negative 1.754 is greater than negative 1.771. Therefore, we cannot reject H0 and conclude that the additive does not reduce fuel consumption. Awesome. So we found that our test statistic, unfortunately, is not less than our rejection value, and so we do not reject H0, and so we let this stay. We assume that mu is still equal to 9.6. We conclude that mu is equal to 9.6. Okay, awesome. So that was question A. Question 2. B. Construct a 95% confidence interval for the true mean fuel consumption of the above model car with a new petrol additive based on the sample data given above. Okay, so literally just going to set up a confidence interval. Now remember, because we're dealing with the sample, standard deviation, and variance, we're going to have to use the T stat, not the Z stat. In essence, you can see that this is essentially the same as the normal confidence interval that we do, the only difference being that there's no Z, but now there's a T, and that there's no sigma, but an S. So the sample, standard deviation. We've got X bar from previous, which was 9.3. Plus minus, we're now going to have to look up this T value as well. Remember, because it's a 95% confidence interval, we're going to have to look up the 2.5%, because remember, it's going to be split, so we want that this entire area between these two values is going to be equal to 95%, and so there'll be 2.5% here, 2.5% here, and so we want to know what value is that over there. Okay, and to do that, we essentially just look at, we remember our degrees of freedom, 13. We're going to be looking up the 2.5% value. And there we go. We've got a 2.160. 2.160. So we're going to have 2.160 times 0.64 over root 14. Okay, all from previous. It's nice and easy. So 9.3 plus. Let's do the lower first. So minus 2.16 times 0.64 divided by root 14. And we end up with a lower value. Let me move this down. We end up with a lower value of 8,931. We do the same for the upper. 9.3 plus 2.16 times 0.64 divided by square root 14. 9.669. Awesome, and there you go. There is our confidence interval, the 95% confidence interval. Awesome. So this has been the TUT questions for week 10. If you have any questions, do ask the tutors, post a comment. If you have any other suggestions or any other requests for videos that you'd like me to do, please also leave a comment, and I'll try to get around as soon as possible. Okay, awesome. All the best. Cheers. Bye.